Hello students, welcome to the online CT classes organized by Jilla Panchayat Udupi. Uh, this is Shyamala Nayak, lecturer in chemistry, Government PU College Bajagoli, and I'll be taking up a topic from chemistry syllabus, that is coordination compounds. Let's begin with the first question. Which one of the following complexes can exhibit geometrical isomerism? As you know very well, geometrical isomerism is nothing but cis-trans isomerism. If you look at the options, the answer options given, the very first complex is of the form Ma2B2 and it is a square planar complex. The second complex is of the form Ma4, where of course M stands for the metal and A for the ligand, and this is also a square planar complex. The third complex is of the form Ma2B2 and it is a tetrahedral complex. The last complex is of the type Ma5B and it is an octahedral complex. Now, see, in order to show cis-trans isomerism, there should be at least two ligands, okay, which are different. Now, in this case, in the square planar complex, the condition is obeyed. You have a central metal and two ligands of one type and two ligands of the other type. So this complex shows a cis-trans isomerism, and the isomers are, this is the cis isomer, okay, this is the cis isomer, two same ligands are on the same side of the metal, and the trans isomer is this, okay, where the two same ligands are on the opposite sides of the central metal. So the first complex shows geometrical isomerism or cis-trans isomerism. What is the problem in the second complex? Actually, all the ligands are of same type here, so it cannot show cis-trans isomerism. Problem with the third complex is that it's a tetrahedral complex. Okay, it's a tetrahedral complex, and in a tetrahedral complex, irrespective of the ligand type, ಅದರಲ್ಲಿ ಸೇಮ್ ಲಿಗ್ಯಾಂಡ್ಸ್ ಇರ್ಬೋದು, ಡಿಫ್ರೆಂಟ್ ಲಿಗ್ಯಾಂಡ್ಸ್ ಇರ್ಬೋದು, ಹೇಗೂ ಇರ್ಬೋದು, because relative positions of the ligands are the same, tetrahedral complexes never show cis-trans isomerism. Okay, this square planar complex doesn't show cis-trans isomerism, and all tetrahedral complexes, remember, do not show cis-trans isomerism. The problem with this octahedral complex is that there is only one chlorido ligand over here. At least there should be two in order to show the cis-trans isomerism. So, Ma5B type of complexes, octahedral complexes, don't show cis-trans isomerism. So, with that, the answer for this particular question becomes option 1, okay, and the hint has already been explained to you. moving on to the next question. This is a question on valence bond theory. Okay, this question is on valence bond theory. They have given you a complex. In the complex, you have got the central metal copper. Is it not? The central metal is copper. You know very well it has the atomic number 29 and the configuration, the outer configuration will be 3D, 10, 4s, 1. But the copper is not present in the atomic form here. It is present in 2+ form. Is it not? It is present in 2+ form because here you have water ligand, aqua ligand, which is neutral. Okay. So what is the configuration of Cu2+? Cu2+ will be, remember one thing, in coordination compounds, most of the questions need the basics, that is configurations of the central metal, which are nothing but the D block elements, transition elements. So configurations are the basis for all these solutions. Now Cu2+ configuration will be 3D 9. Is it not? You have to remove 2 electrons, one from here and one from here. So that makes it 3D 9. It is given that this particular complex has one unpaired electron. So how do you write the box diagram for this configuration? Even if it is not given that one unpaired electron is present, it is understood. Okay. For D9 configuration, you cannot have any other choices. The configuration, the box diagram for the configuration will be, first you have to fill 1 electron each. Okay, there are 5 d orbitals, 1 electron each has to be filled, and then the pairing starts. So it will be 6th here, 7th electron, 8th, and here comes the 9th electron. So we are left with only 1 electron, which is given in the question. Now, which of the following statements are true? That is your question, and the options are: the complex is octahedral. Let's see whether the complex is octahedral. It all depends on the hybridization, is it not? Now, for copper 2+, in this complex, none of the 3D orbitals are available for hybridization. Ella 3D orbitals electron in the occupy ಆಗಿರುವ ಕಾರಣ hybridization ಗೆ ಇದ್ಯಾವುದು ಸಿಗುವುದಿಲ್ಲ. So we have to take the next orbitals for hybridization. ಎಷ್ಟು orbitals ಬೇಕು? Actually we need 6 orbitals for hybridization because there are 6 ligands. So the first 6 vacant orbitals will be what? It will be 4s, then comes 4p, 4 orbitals are over, and I need to take 2 orbitals from 4d. There are 5 actually. Okay, there are 5. I need to use only 2 orbitals from 4d. So that makes it which hybridization? sp3d2 hybridization. Is it not? sp3d2 hybridization. So if this is the hybridization, then you know very well the shape of the complex will be octahedral. So the first option, I mean this question, number 1 statement is correct. The complex is D2sp3 hybridized. That is wrong because it is not D2sp3, it is sp3d2. 3d orbitals are not involved in the hybridization. Instead, 4d orbitals are involved. That is why sp3d2. So this one is wrong. The third statement says the complex is an outer orbital complex. That is correct because instead of 3D, 4D orbitals are involved in hybridization and in bonding with the ligands. If 3D were to be involved, then the complex would have been inner complex. But 4D is involved, that is why the complex is outer complex. The complex is diamagnetic. This is wrong. Why it is wrong? Because there is one unpaired electron. It is given in the very question itself, is it not? There is one unpaired electron in the complex, so the complex cannot be diamagnetic. It should be paramagnetic. Okay, so the true statements are, statement 1 and statement 3. Is it not? Statement 1 and statement 3. Let's check it with the answer. Yeah, option 3 is the correct answer. And the hint is already explained to you. Moving on to the next question. This question is based on crystal field theory. In complexes, actually, while studying complexes, we sometimes take the help of valence bond theory and some other times crystal field theory. Remember one thing, if the theory is mentioned in the question, then we have to make use of that approach only. But if nothing is mentioned, most of the times VBT works out. Okay, it's better to take VBT and solve the questions. Okay, now it is CFT and the question is, how many unpaired electrons are there in strong field iron second octahedral complex? So let me take iron. It has the atomic number 26, configuration 3D 6 4s2. Is it not? 3D 6 for 26. This is how we remember. But this is not atomic iron. It is iron 2, that is Fe2 plus. That is why the configuration changes to 3D 6. These 2 electrons are gone and the configuration becomes 3D 6. Because the theory is crystal field theory, now we should consider crystal field splitting concept. And the complex is given to be an octahedral complex. Okay, that is why in octahedral complexes, actually, how does the crystal field splitting take place? How does it happen? The 5 degenerate d orbitals, when the ligands come near them, they split into 3 T2G orbitals, is it not? 3 T2G orbitals of lower energy and 2 EG orbitals of higher energy. Of course, in the case of tetrahedral complexes, the reverse happens. Because here we have octahedral complexes, this is the pattern. Lower energy TG and higher energy EG. Okay, now the configuration is D6, is it not? So how do you fill these orbitals with 6 electrons? Remember, it's a strong field. Okay, strong field is present. That is strong ligands, strong field ligands are coming near iron 2. So this energy gap will be very high. The energy gap between T2G and EG will be very high. So what do the electrons do? Instead of going to higher energy EG, they prefer to stay with T2G. So electron pairing is going to happen here. First 3 electrons go to T2G without any doubt. But the next 3 electrons, there are totally 6. Next 3 electrons also stay with T2G only. Okay, pairing happens. They don't want to go to EG because the energy gap here is very, very high. So this is the configuration. Okay, T2G6 EG0 is the configuration, and therefore number of unpaired electrons. Can you see any number of? Can you see any unpaired electrons here? No, all the electrons are paired. So number of unpaired electrons is 0. So what is the answer? Option 1 has to be the answer. Okay, option 1 is the correct answer. Yeah. Next, let's move on to the next question. Again, it's a question on crystal field theory. Now, the complex given is a manganese complex, and manganese is present in which form? Mn2+. Manganese is 25. That means it is 3d5, 4s2, but because it is 2 plus, these 2 electrons have to be removed. Okay, so it is 3d5. It is given that it contains 5 unpaired electrons. Okay, 5 unpaired electrons. So how do you write the configuration? This is T2G. Okay, this is EG. In order to accommodate 5 unpaired electrons, we have to send the 3 electrons here and 2 more electrons here. Now, why doesn't the pairing happen? Why do the electrons go to EG? That's because you have equiligands, which are weak ligands, weak field ligands. Okay, so this gap, this energy gap is going to be very less, so the electrons can go to EG. Okay, they prefer to go to EG rather than getting paired up in T2G. Alright, even otherwise it's given in the question 5 unpaired electrons, so you don't have to bother about the type of ligand present. Now, we have to pick the true statements, is it not? Which response includes all the statements that are true and no false statements. So, we have to pick the true statements. Let's check the first statement. It is diamagnetic. The complex is diamagnetic. It is wrong, totally wrong. Why? Because you have all the 5 unpaired electrons. Okay, all the 5 unpaired electrons. So, the complex ought to be paramagnetic. It is not diamagnetic. It is a low spin complex. That is also wrong. Because of the presence of 5 unpaired electrons, okay, the complex is a high spin complex. Ella unpaired electrons idre, the complex becomes high spin, or you can also call it free spin, is it not? Because unpaired electrons are there, it's a free spin or high spin complex. So the second statement is also wrong. It's a D5 ion, that's correct. Okay, the configuration is D5. So this statement is correct. It is octahedral. That is also correct because you have a D5 system here, and in order to accommodate 6 ligands, these d orbitals are not available. Okay, they contain unpaired electrons. No, they are not available to accommodate the ligand electrons. That is why we have to take up the next orbitals. Which are they? 4s, 4p, and 2 from 4d. Okay, 6 ligand electron pairs anna accommodate ಮಾಡಲಿಕ್ಕೆ ನಮಗೆ 3d ಸಿಗೋದಿಲ್ಲ, 4s 4p 4d ಅನ್ನ ತಗೊಳ್ಬೇಕಾಗತ್ತೆ. So the hybridization is sp3d2, which means the geometry is octahedral. Okay, there are 6 ligands, that is why the geometry is octahedral. So this statement is correct. So with that, which is the right answer? Statement 3 and statement 4 are correct. Is it not? Statement 3 and statement 4 are correct. So option 2 becomes the right answer. Yeah, option 2 is the right answer. Again, a question on crystal field theory. Now you have two complexes. Both are the complexes of chromium, and in both the complexes, chromium is present in which form? It is present in 3+ form. Okay, 3+ form. Because water is neutral here and Cl3 will have a -3 charge. So to neutralize it, chromium should have +3 charge. Even here the same thing. Ammonia, ligand name is amine. So this is also neutral. This is -3. So chromium should be +3. Now in 3+ form, what is the configuration of chromium? It is 24, has unusual configuration, correct? 3d5, 4s1 in the atomic state. In the 3+ state, what happens is 1 electron from here and 2 from here are removed and the configuration becomes 3d3. Okay, 3d3. So with this configuration, let's try to understand the statements, and we have to pick the false statement. Remember, both chromium metal ions are paramagnetic with unpaired electrons. That's true, because when you have a 3 configuration, if you expand it and write in the form of T2G and EG, okay, it's an octahedral complex. Both the complexes are octahedral. So T2G, lower energy, EG, higher energy. Now, irrespective of the ligand that is present, water is actually a weak field ligand and ammonia is a strong field ligand, comparatively strong field ligand. But here, bari 3 electrons iruva karana, weak field ligand irli, strong field ligand irli, what happens is the 3 electrons occupy the 3 T2G orbitals. Okay, ligand type illi matter agudilla. So all the 3 are unpaired electrons, and that is why the complex, both the complexes, okay, they are paramagnetic. 3 unpaired electrons iruva karana complex is paramagnetic. Look at the second statement. So this first statement is correct. Looking at the second statement, delta oct. Delta here is nothing but crystal field stabilization energy. So this energy, how do you calculate this energy? Crystal field stabilization energy is not actually energy of a light absorbed by the complex. Is it not? CFSE is not actually the energy of light absorbed by the complex while its electron does the transition. Instead, it is equal to energy of complementary color. Okay, it is the energy of complementary color. color which is complementary to the absorbed light color. That means if a particular complex is violet colored, on the complex ಗೆ violet color idre, ಅದರ CFSE violet color na energy ಗೆ ಸರಿ ಇರುವುದಿಲ್ಲ. What will be CFSE then? It will be the energy of the complementary color. Violet na complementary color is somewhat yellow. That is why CFSE CFSE in the first case will be energy of yellow light, not violet light. And in the second case, what is the color of the complex? It is yellow. So CFSE is not equal to yellow energy. It is equal to energy of the complementary color, that is violet. ಈಗ second statement ಅಲ್ಲಿ this particular complex is being talked about. ಅದರ color ಏನು? It's yellow. CFSE cannot be calculated from the yellow light energy. Is it not? It cannot be calculated from yellow light energy. Instead, it has to be calculated from which colored light? Violet. Okay, yellow du complementary anta helidre hatra violet irutte. So CFSE will be energy of violet colored light. Okay, so with that, this particular statement becomes wrong. Coming to the third statement, CFSE of chromium complex with water ligand is less than CFSE of chromium complex with ammonia ligand. That's true actually, because as I already told you, this is a weak field ligand, whereas this is a strong field ligand. Idra crystal field stabilizing strength enide adu ಜಾಸ್ತಿ ಇದೆ, ಹಾಗಾಗಿ ಅದು ಜಾಸ್ತಿ ಸ್ಪ್ಲಿಟ್ಟಿಂಗ್ ಮಾಡುತ್ತೆ crystal field ಅನ್ನ, and the energy will be high. The last statement says the two complexes absorb their complementary colors. That is true. Is it not? I've already explained it. This statement is correct. So only false statement is the second statement. With that, option 2 is the answer. Now coming to the sixth question. This is actually a problem. Excess of silver nitrate solution is added to 100 ml of 0.01 molar complex solution. Okay, they've given you a complex. Let's write that complex. Penta aqua. There are 5 water ligands. Chlorido, chromium, chloride. Now, how many chlorides that we have to find out here? Chromium, oxidation status +3. It's given. Water, you know, is neutral. The Cl is -1. Okay, so +3 and -1. Mix it, +2. In order to neutralize +2, here we need -2 for chlorines. That is why there should be 2 chlorines. Okay, writing this part correctly is the key point. They'll not give you dichloride, remember. Okay, they'll not give you dichloride. You only have to write here the correct number by tallying all these charges. So once you have this number, what does it mean? This particular complex has two ionizable chlorines. Okay, the complex has two ionizable chlorines. You know very well that any coordination compound or complex ionizes only here, that is outside the square bracket, which is called coordination sphere. And inside, the ionization is not possible because there are coordinate bonds within the square bracket. Ionization is not possible. Ionization takes place only outside the square bracket or coordination sphere. So when the complex ionizes, how many chloride ions you get? For 1 mole of the complex, okay, for 1 mole of the complex, you're getting 2 chloride ions. And those chloride ions, they react with the silver nitrate solution and they form silver chloride. Is it not? So how many moles of silver chlorides will be formed? 2 moles. 2 chlorides iruva karana, 2 silver chloride, that is 2 moles of silver chloride will be formed. In case there is 3 moles of silver chloride will be formed. If there is only 1, then 1 mole of AgCl will be formed. Okay. Now, in the question, they have not given you 1 mole of the complex, but they have given 100 ml and 0.01 molar solution of the complex. Idralli ಎಷ್ಟು moles ಇರುತ್ತೆ? 100 ml 0.01 molar ನಲ್ಲಿ how many moles of the complex will be there? You have to divide by 1000. Okay, that comes out to be how much? It comes out to be 10 to the power of minus 3. Is it not? 10 power minus 3. So many moles. Okay, 10 power minus 3 moles ನಷ್ಟು ಕಾಂಪ್ಲೆಕ್ಸ್ ಪ್ರಾಬ್ಲಮ್ ಅಲ್ಲಿ ಇದೆ. ಈಗ ಇದಕ್ಕೆ ಎಷ್ಟು ಸಿಲ್ವರ್ ಕ್ಲೋರೈಡ್ ಫಾರ್ಮ್ ಆಗುತ್ತೆ? It is just cross multiplication, that is 2 into 10 to the power minus 3 mole. Okay, 2 into 10 to the power minus 3 mole divided by 1 makes it the same. But the answer is not given in terms of moles. Moles alle answer kottidre, this would have been the answer. Adre mole alli answer illa, instead the answer is in grams. So next you have to convert this mole to grams. How do you do that conversion? Silver in atomic mass anna kottidare, so let's use that. It is 108. And Cl, you know very well, is 35.5. Okay, that's nothing but 143.5. So 1 mole silver chloride anta helidre 143.5 grams. But nam hatra 2 into 10 power minus 3 moles ide. Hagagi this becomes what? This becomes 2 into 10 power minus 3 into 143.5 grams. Okay, 2 into 10 power minus 3 into 143.5 grams. So let's check for the answer. 2 into 143 is of course 287, and there is a 10 power minus 3. Okay, 287 into 10 power minus 3 grams. Moles alli kelidre you can stop here, but because it is asked in mass, in grams, you have to go one step further. So this will be the answer. Option 1 is the right answer. Coming to the next question, the 7th question. This is a question on EDTA. What is the full form of EDTA? It is ethylene diamine tetra acetic acid or tetraacetate. How do you write the structure of EDTA ligand? It is ethylene, CH2CH2, diamine, there are two nitrogens, and tetraacetate, CH2COO minus groups are present in 4 numbers. So this is your EDTA ligand. Okay, it has come from ethylene diamine tetraacetic acid. Actually, it is tetraacetate. Now, there are actually 6 donor atoms, 2 nitrogens and 4 O minus ions. So EDTA is a hexadentate ligand. Its denticity is 6. Now the question is, how many such molecules are needed to make an octahedral complex? In order to form an octahedral complex, we need how many ligands? We need 6 ligands, provided they are monodentate. Octahedral complex ಮಾಡಲಿಕ್ಕೆ 6 ligands ಬೇಕು. ಯಾವಾಗ 6? When they are monodentate. But ಈಗ you have a hexadentate ligand. 6 donor atoms ಇರುವ, okay, at a time 6 electron pairs ಅನ್ನ donate ಮಾಡುವ capacity ಇರುವ hexadentate ligand ಇದೆ. That is why only one such ligand is enough. 6 monodentate ligands ಹೇಳಿದ್ರು ಒಂದೇ, 1 hexadentate ligand ಹೇಳಿದ್ರು ಒಂದೇ. So only one EDTA molecule is enough for forming octahedral complex. Option 3 is the right answer. Moving on to the next question. In which of the following octahedral complexes of cobalt will the magnitude of delta O be the highest? Delta O stands for crystal field splitting energy in the case of octahedral complexes. Okay, so the magnitude is highest in which complex is the question. Crystal field stabilization energy depends on many factors. It depends on the central metal that you have. It also depends on the oxidation state of the central metal, and it depends on the type of ligand that is present. Now, the first 2 factors here are the constants, because in all the 4 options you have cobalt complex, is it not? The central metal is cobalt only. And in all the 4 options, the cobalt is present in CO3 plus form. So oxidation state of cobalt is also the same in all the 4 cases. So the first 2 factors are not going to influence delta O. In this case, only the ligand type is going to matter. So let's check only with the ligands. The first ligand that you have is the oxalato ligand, ox ligand, and then you have aqua ligand, then you have amine, and you have cyanido, Cn minus. If you look at the spectrochemical series, which gives you the order of ligands for their crystal field stabilizing or splitting strength, you will see that oxalato lies at the left extreme, okay? Among these 4, oxalato has the least power of crystal field splitting, then comes aqua, then comes amine, and finally comes cyanido. That is why this is a strong field ligand, and hence the complex formed by it will have the highest delta O. So option 4 is the correct answer. Okay, now we have a nickel complex, and the complex is NiX4 2 minus. The ligand X, okay, that is unknown, but it is given that it's a monodentate ligand and uni-negative. Andre X is present in X minus form, just like a Cl minus or Br minus, F minus, okay. The question is to find out the unpaired electron number and the shape of complex. So how to do it? Which approach shall we follow? It's better to follow VBT, okay? Unless it is mentioned, we follow valence bond theory for solving such questions. So let me take up the central metal ion. Nickel is the central metal, but it is present in which form? Ni2 plus. Because this is uni-negative. There are 4 such uni-negative ligands, so that makes it minus 4. Okay. In NiX4 2 minus, the charge contribution from this is minus 4. So if you take it as X minus 4 is equal to minus 2. X is 4 minus 2, that is 2. So nickel is in 2 plus form. Now, what is the configuration of Ni2 plus? Nickel is 28. So configuration is 3D8 and 4 is 2. Ni2 plus will be just 3D8. These 2 electrons will be gone, so 3D8. Now, how do you write the box diagram for this configuration? I'll take 5 d orbitals. Okay, which d orbitals are those? They are 3D. First, I'll give single electrons. Now, 3 more electrons are there that I'll pair. Okay. It is given that the complex is paramagnetic. That means what we have written is correct. Okay. The ligand X minus doesn't bring about a pairing. Paramagnetic anta ಕೊಟ್ಟಿರುವ ಕಾರಣ ನಾವು ಬರೆದ ಕಾನ್ಫಿಗರೇಷನ್ ಸರಿ ಇದೆ. ಈ 2 electrons pair ಆಗುವುದಿಲ್ಲ. Strong field ligand ಇಲ್ಲ. Okay. Now how many unpaired electrons are there? It's very clear that there are 2 unpaired electrons. Okay. There are 2 unpaired electrons. Now what is the geometry of the complex? 3D is full. There is no space. After 3D comes 4s and then comes 4p. There are totally 4 ligands. Is it not? We have to accommodate 4 ligands, for which we need 1, 2, 3, 4 vacant orbitals. They are S and 3 p orbitals. That is why the hybridization is going to be, it's going to be sp3. Is it not? Hybridization is going to be sp3, and whenever the hybridization is sp3, the shape of the complex, you know, is a tetrahedral. Okay. So unpaired electrons are 2 and the shape is tetrahedral. Okay. 2 unpaired electrons and the shape is tetrahedral. So option 2 is the correct answer. All right. The hint we have already seen. Moving on to The next question. Okay, this is a question on magnetic moment. So what is the formula for magnetic moment? It is mu is equal to square root of n into n plus 2 Bohr magneton, Bm, the unit. So it's very clear from the formula that magnetic moment depends on n. What is that n? It is the number of unpaired electrons. Now, in order to have the highest magnetic moment, the complex must possess highest number of unpaired electrons. So magnetic moment ಎಲ್ಲದಕ್ಕೂ ಲೆಕ್ಕ ಹಾಕಿ ಕೂತ್ಕೊಳ್ಬೇಕಾಗಿಲ್ಲ. It is enough if you find out unpaired electrons. ಯಾವುದರಲ್ಲಿ ಜಾಸ್ತಿ unpaired electrons ಇದೆಯೋ ಅದರಲ್ಲಿ magnetic moment ಕೂಡ ಜಾಸ್ತಿ ಇರ್ತದೆ. The first complex is CO3 plus complex. Cobalt is 27 actually. 3D 7 4s 2, but 3 plus means it will be 3D 6. Now, how do you write the box diagram for 3D 6? It is 5 electrons like this, and the sixth one gets paired up. Because flow is a weak ligand, pairing ಮಾಡೋದಿಲ್ಲ. So electrons ಹೀಗೆ ಇರುತ್ತೆ. Okay, pairing ಆಗಲ್ಲ. They don't go against Hund's rule. ಇದೇ ತರ ಇರುತ್ತೆ. ಹಾಗಿದ್ರೆ what is the number of unpaired electrons? It is nothing but 4. Okay, n is 4. In the second complex, which is also CO3 plus, ಅದು ಕೂಡ CO3 plus box diagram ಇದೇ ತರ ಬರುತ್ತೆ. 5 electrons hige, and the sixth one paired. But the thing is, amine ligand with respect to cobalt, amine ligand with respect to cobalt is a strong ligand, strong field ligand. Adu pairing ಮಾಡುತ್ತೆ. ಇಲ್ಲಿ pairing ನಡೀತದೆ. As a result, you end up with this particular configuration. Pairing ಆಗಿ configuration ಈ ತರ ಆಗುತ್ತೆ, and unpaired electron number is 0. In the first case 4, second case 0. The third complex is a Ni2 plus complex. Ni2 plus is 3D8, is it not? Ni2 plus is 3D8, so the box diagram will be first 5 single electrons, then 3 electrons get paired up. So this is 3D8. Again, you have amine ligands. Amine ligands have a strange property, that is, in general, they are a medium field ligand. With respect to cobalt, they act as a strong field ligand, but with respect to nickel, they act like a weak field ligand. So cobalt na jotege electron pairing naditade, but nickel nalli electron pairing nadiyudilla. That is the speciality of amine ligand. Okay, so illi electron pairing nadiyudilla. So we have 2 unpaired electrons. N is equal to 2. What happens in the case of last complex? Last complex nalli kuda which central metal ion we have? We have Ni2 plus. Okay. Adre ligands matra bere ide. Let me write here. We have in the last complex Ni2 plus 3D8. First 5 electrons, then 6th, 7th and 8th. So this is the configuration, but because there is a cyanidoligand, which is a very strong field ligand, these 2 electrons are paired up, and here also what happens? Electrons pair up agi unpaired electron number 0 agi bidutte. So highest unpaired electrons irodu very first complex alli, is it not? Very first complex has highest unpaired electrons. That is why, okay, that is why what happens is first option itself becomes the right answer. So you can see in the hint, first complex has 4 unpaired electrons, second and the fourth have no unpaired electrons, and the third complex has 2 unpaired electrons. So highest being 4, that is the answer. Thing to note from this particular question is NH3 is a medium field ligand. Cobalt na jotege it brings about pairing, and nickel na jotege it doesn't bring about pairing. Again a question on magnetic moment. This time the magnetic moment is given to you. In the previous question magnetic moment was asked. Okay, here the magnetic moment is given and you have to find out the complex here. So the first complex has Cu2 plus at the center. The configuration is 3D9. Copper is 3D10, 4s1, Cu2 plus becomes 3D9. 3D9 is this. Okay, how many unpaired electrons are there? There is 1. Only this is unpaired. The second complex is of Ni2 plus. See, in the case of 3D9, whether you have weak field ligand or strong field ligand, it doesn't matter. 3D9 configuration idaga bere choices illa. Ide configuration. But now you have a choice Ni2 plus 3D8 bariyuvaga. Originally, we write the configuration like this. This is 3D8. This is unpaired untu. Adre cyanide ligand iruva karana. Ee eradu ligand, I mean, ee eradu electrons kuda pair up agate and unpaired electrons become 0. Then the third complex is of Ti4 plus, is it not? Titanium tetrachloride. This is 4 minus, titanium becomes 4 plus. Titanium comes after scandium, it is 22, 3D2, 4s2, but 4 plus ant helidre, ee ella electrons, they are lost. So the configuration becomes 3D0. So no question of unpaired electrons. Okay, there are no unpaired electrons. Electrons themselves are not there, so unpaired electrons is also 0. Coming to the last complex, illi cobalt 2 plus formal ide. Is it not? This is minus 6. So only if cobalt is 2 plus enagataga, minus 6 and 2 makes it minus 4. So cobalt is present in 2 plus form. That means it is having 3D7 configuration. Alva CO3 plus nalli cobalt 3D6 configuration ittu. Iga 2 plus alli 3D7. If you write the box diagram, it will be 5 electrons, the 6th and the 7th electron. They are paired up. The ligand is a weak field ligand, pairing madudilla, so N is equal to 3. First case N is 1, next two cases 0, and the third case N is 3. Iga magnetic moment is 1.73. Okay, magnetic moment is given to you. The formula for it is N into N plus 2. Let me do it by trial error method. I'll substitute N as 1. What do I get? I get mu as 1 into 1 plus 2, that is square root of 3, which is nearly equal to 2 but less than 2. Alva, square root of 4 andre 2. Square root of 3 andre 2 ge hatra irate but slightly less than 2, which can be 1.73. Alva. 1.73 ಆಗುವ ಎಲ್ಲ ಚಾನ್ಸ್ ಇದೆ. ಹಾಗಾಗಿ n is equal to 1 matches with the magnetic moment value. 1 unpaired electron idre namge magnetic moment 1.73 sigate. So in which case we had n is equal to 1? We had it in the, if I'm not wrong, we had it in the very first case. Correct? In the very first case, we got the value as n is equal to 1. That is why that itself is the answer. Okay, n is equal to 1 was got in the first case. So that is the answer. The next one is again a problem. Now, a complex is given to you. That particular complex, when reacts with silver nitrate solution, okay, the complex when reacts with silver nitrate solution, it gives silver chloride. That means there are some ionizable chlorines in the complex. Okay, silver chloride formation ಆಗ್ತಾ ಇದೆ ಅಂತ ಹೇಳಿದ್ರೆ ಕೆಲವು ionizable chlorines ಇದ್ದೇ ಇದೆ. ಅದು ಎಷ್ಟು ಅಂತ we have to find out. Only then we can write the formula of the complex. ಎಷ್ಟು ionizable chlorines ಇದೆ ಅಂತ ಗೊತ್ತಾಗಿಬಿಟ್ರೆ then we can write the formula of the complex. Okay, so I'll make two columns, complex ಮತ್ತೆ AgCl. ಕಾಂಪ್ಲೆಕ್ಸ್ ನ ಮಾಸ್ ಕೊಟ್ಟಿದ್ದಾರೆ 2.675 ಗ್ರಾಮ್. ಅದು ಫಾರ್ಮ್ ಮಾಡುವ AgCl ನ ಮಾಸ್ ಕೂಡ ಕೊಟ್ಟಿದ್ದಾರೆ 4.78 ಗ್ರಾಮ್. ನನಗೆ ಏನ್ ಬೇಕು, ಎಷ್ಟು AgCl ನ ಮೋಲ್ಸ್ ಫಾರ್ಮ್ ಆಯ್ತು ಅಂತ ಬೇಕು. ಈಗ 2 moles AgCl ಫಾರ್ಮ್ ಆದ್ರೆ the meaning is 2 ionizable chlorines are present. 4 moles AgCl ಫಾರ್ಮ್ ಆದ್ರೆ 4 ionizable chlorines ಇದೆ ಅಂತ ಅರ್ಥ. So what I need to find out is how many moles of AgCl are formed. So for this I have to convert this into moles, is it not? They've given you the molar mass of the complex 2.675 ಅನ್ನ molar mass ಇಂದ ಡಿವೈಡ್ ಮಾಡ್ತೇನೆ. ಓಕೆ, 267.5 ಆಗುತ್ತೆ. So this will be ಇದು ಈಗ ಗ್ರಾಮ್ಸ್ ಅಲ್ಲಿ ಇದೆ. ಐ ವಾಂಟ್ ಟು ಕನ್ವರ್ಟ್ ಇಟ್ ಇನ್ ಟು ಮೋಲ್ಸ್. 2.675 divided by 267.5. This is because it is the molar mass of the complex. That comes out to be 0.01 mole. Okay, 0.01 mole. Idanna kuda I'll convert to moles. 4.78 grams ಇದೆ. 4.78 ಗ್ರಾಮ್ ಅನ್ನ ಮೋಲಿಗೆ ಕನ್ವರ್ಟ್ ಮಾಡಲಿಕ್ಕೆ ಮೋಲಾ ಮಾಸ್ ಇಂದ ಡಿವೈಡ್ ಮಾಡಬೇಕು. ಮೋಲಾ ಮಾಸ್ ವ್ಯಾಲ್ಯೂ ಕೊಟ್ಟಿದ್ದಾರೆ 143.5. That's nothing but, you can guess, okay, it's nothing but 3. I mean, not exactly 3. It's how much? It's 0.03. ಸರಿಯಾ? ಇದನ್ನು ಮೋಲ್ಗೆ ಕನ್ವರ್ಟ್ ಮಾಡಿದೆ, ಇದನ್ನು ಮೋಲ್ಗೆ ಕನ್ವರ್ಟ್ ಮಾಡಿದೆ. ಸೊ 0.01 ಮೋಲ್ ಕಾಂಪ್ಲೆಕ್ಸ್ ಇದ್ದು 0.03 ಮೋಲ್ ಸಿಲ್ವರ್ ಕ್ಲೋರೈಡ್ ಕೊಟ್ಟಿದೆ. ಹಾಗಿದ್ರೆ 1 mole of the complex, okay, 1 mole of the complex ಎಷ್ಟು ಕೊಡುತ್ತೆ? Zero 0.01 ಗೆ 0.03 ಆದರೆ 1 mole ಗೆ it will be 3 mole. 1 mole of the complex will give you 3 moles of AgCl. From this it is very clear that there are 3 ionizable chlorines. 1 mole of complex 3 AgCl moles ಅನ್ನ ಕೊಡ್ತಾ ಇದೆ ಅಂತ ಹೇಳಿದ್ರೆ the meaning is there are 3 ionizable chlorines. Okay, so what is the answer? How do you write the formula of the complex with the 3 ionizable chlorines? It should be option number 1. Alva, square bracket na horagade, coordination sphere na horagade, 3 chlorines barabeku. Idralilla, idral onde chlorine ide. Here you do not have any chlorines. Here you have only 2 chlorines. But in the first option, there are 3 chlorines outside the square bracket. That is why option number 1 is the answer. So, mass alidda problem anna moles ge convert ಮಾಡ್ಕೊಂಡ್ರೆ ಆಯ್ತು. Okay, coming to metal carbonyls now. There are 4 metal carbonyls in front of you, and the question is, which metal carbonyl has the least CO bond order? See, in metal carbonyls, what happens is between metal and carbon, metal matte carbon na naduve, actually a special type of bonding is present. A bond is formed by the donation of electron from the ligand to the metal. Not only that, also there is a back bonding. Okay, this particular bond has got dual nature. It has sigma character, which is because of the donation of electrons from ligand to metal. Also, it has some pi character, which is because of back bonding. Metal na filled orbitals in the electrons lateral overlapping agate ligand orbitals na jotege. So sigma character na jotege there is some pi character also due to back bonding. This particular bond is a special bond. Okay, now let's have a look at MC bond, metal and carbon bond in all the 4 cases. First is, in first case, the metal is manganese. It is 3D5,4S2. But it is not present in Mn form. It is Mn plus because carbonyl is neutral. Okay, so Mn has the charge Mn plus. So the configuration becomes 3D5,4S1. Since the carbonyl ligand is a very strong field ligand, just like cyanido ligand, idu kuda strong field ligand ಆದ ಕಾರಣ ಇಲ್ಲಿ electron pairing ಆಗತ್ತೆ. 3D5,4S1 ಇದದು electron pairing ಆಗ್ಬಿಟ್ಟು 3D6 ಆಗತ್ತೆ. 3D6 ಹೇಗಿದೆ actually ಇಲ್ಲಿ 3 electron pairs are present. Okay, all the 6 electrons by the influence of carbonyl ligand, they are forming electron pairs. In the next case, iron is the central metal. It is 3D6,4S2. Iron is present in atomic state only. ಆಯ್ತಾ, ಇಲ್ಲಿ ಯಾವುದೇ ಚಾರ್ಜ್ ಇಲ್ಲ. ಕಾರ್ಬೋನಿಲ್ ಕೂಡ ನ್ಯೂಟ್ರಲ್, ಹಾಗಾಗಿ iron atomic state ಅಲ್ಲೇ ಇದೆ. ಇಲ್ಲಿ ಕೂಡ ಕಾರ್ಬೋನಿಲ್ನ ಇನ್ಫ್ಲೂಯೆನ್ಸ್ ಇಂದ electron pairing ನಡೀತದೆ against Hund's rule. And you get how many electron pairs here? 4 electron pairs are got. In the next case, chromium, again metal in the atomic state. Okay, chromium nalli kuda chromium is 24, 4 3D 5 4s 1 carbonyl influence indagi 3D 6 ಆಗುತ್ತೆ 3 electron pairs okay single electrons ಇರುವುದಿಲ್ಲ. Next you have V minus ಇದೆ vanadium is 23 3D 3 4s 2 but V minus ಇರುವ ಕಾರಣ ಒಂದು electron extra ಉಂಟು. It makes it 3D 4 3D 4 4s2 carbonyl ಇರುವ ಕಾರಣ ಅದರ influence ಇಂದ it becomes 3D 6. ಈ ಎರಡು electrons ಕೂಡ d orbitals ಗೆ ಹೋಗಿ ಅಲ್ಲಿ electron pairing ನಡೀತದೆ. How many electron pairs? 3 electron pairs. So remember, in all these complexes electron pairing is due to the influence of the strong ligand, that is carbonyl. Now in which case maximum number of electron pairs are seen? That is in this case, in the second case. Second case alli electron pairs ಜಾಸ್ತಿ ಇದೆ 4 electron pairs ಇದೆ. Naturally the metal and carbon bonding, okay, carbonyl na carbon ಮತ್ತೆ metal na ನಡುವಿನ bonding is very strong when there are maximum number of electron pairs. Metal nalli ಜಾಸ್ತಿ electron pairs iddaga this bond becomes strong. When this bond becomes strong, the bond between carbon and oxygen becomes weak. ಈ ಕಾರ್ಬನ್ ಈ ಮೆಟಲ್ನ ಜೊತೆಗೆ ಜಾಸ್ತಿ ಇಂಟರಾಕ್ಷನ್ ನಲ್ಲಿ ಇದ್ದಾಗ ಬಿಸಿ ಇದ್ದಾಗ ಕಾರ್ಬನ್ ಅಂಡ್ ಆಕ್ಸಿಜನ್ ನಡುವಿನ ಬಾಂಡಿಂಗ್ ಸ್ವಲ್ಪ ವೀಕ್ ಆಗುತ್ತೆ. And so in the case of second complex you have a strong bond between Fe and C and a weak bond between C and O. So C and O bond order is lower, bond weak andre bond order is lower, kadime. That happens in the second case. Okay, just the electron pairs ide, metal carbon bonding strong ide, carbon oxygen bonding weak ide. So the option 2 is the right answer. Okay. In the next question, we have two complexes. One is a carbonyl complex of nickel, another is a cyanido complex of nickel. Let's find out the oxidation states of the metals first. In the first case, nickel is present in the atomic state, carbonyl ligand neutral, ada karana nickel 3D 8 4s2 formally unto. And in the second case, nickel is present in 2 plus form, that is 3D 8. ಈ ಎರಡು electrons ಹೋಗಿದೆ 3D 8. Okay. So the first statement is wrong. Nickel is in the same oxidation state in both. That's wrong. In the first case, nickel is neutral. In the second case, it is 2 plus. So the first statement is wrong. The rest of the statements are on the shapes or the geometries of the complex. So let's find out the geometry. In the first complex, you have this configuration, and because carbonyl is a strong ligand, I've already told you that electron pairing is brought about and the configuration becomes 3D10. Okay, configuration becomes 3D10. As a result, in order to accommodate the 4 ligands, we have to make use of 4s and 4p orbitals. 3D available illa, 4 ligands ide, adanna accommodate marlikke ಈ 4 orbitals ಬೇಕು. So hybridization is sp3. Okay, hybridization is sp3. That means the geometry should be tetrahedral. And in the second case, you have cyanido ligand. Cyanido ligand kuda strong enough ಸೊ ಇಲ್ಲಿ ಕೂಡ ಇಲೆಕ್ಟ್ರಾನ್ಸ್ ಅಗೇನ್ಸ್ಟ್ ಹುನ್ಸ್ ರೂಲ್ ಪೇರ್ ಆಗಿರುತ್ತೆ. 3d8 ಅಂತ ಹೇಳಿದ್ರೆ ಈ ತರ ಪೇರ್ ಆಗಿರುತ್ತೆ. ಆದ್ರೆ ಒಂದು ಡಿ ಆರ್ಬಿಟಲ್ ಹೈಬ್ರಿಡೈಸೇಷನ್ಗೆ ಅವೈಲೇಬಲ್ ಇರುತ್ತೆ. ಓಕೆ, ಇಲ್ಲಿ ಅವೈಲೇಬಲ್ ಇರಲಿಲ್ಲ. D10 ಅಂತ ಹೇಳಿದ್ರೆ ಆಲ್ 3d ಆರ್ಬಿಟಲ್ಸ್ ಆರ್ ಎಕ್ಸಾಸ್ಟೆಡ್. ಬಟ್ ಇಲ್ಲಿ ಒಂದು ಅವೈಲೇಬಲ್ ಇದೆ. This is the second one, this is third and fourth. So hybridization is dsp2 rather than sp3. It is dsp2 and geometry, as you know very well, is square planar. dsp2 hybridization idre geometry becomes square planar. Okay, they have tetrahedral and square planar geometry respectively. This statement is correct. Both have tetrahedral, wrong. Both have square planar, wrong. So correct statement is the last one. Yeah, option 4 is the correct answer. Next question, a question on magnetic moment. The value of spin-only magnetic moment for one of the following configurations is 2.84 bm. The correct one is, mu value is given. Formula for mu is square root of n into n plus 2. We have already found out that when n is equal to 1, mu value comes out to be 1.73. Is it not? In one of the previous problems we have done it. Now when n is equal to 2, what happens? Let us see. Mu is equal to 2 into 2 plus 2, 2 into 4, that is root 8. You know that square root of 9 is 3. So square root of 8 should be nearly equal to 3 but slightly less than 3. That matches with our 2.84. Alva? So illi n is equal to 2 namma mu value jotege match agate. So how many unpaired electrons are there? If mu is 2.84, it is 2. ಈಗ ಈ 4 ಆಪ್ಷನ್ಸ್ ಅಲ್ಲಿ ಯಾವುದರಲ್ಲಿ 2 ಅನ್ಪೇರ್ಡ್ ಎಲೆಕ್ಟ್ರಾನ್ಸ್ ಇದೆ ಅಂತ ನಾವು ಫೈಂಡ್ ಔಟ್ ಮಾಡಬೇಕು. ಲೆಟ್ಸ್ ಟೇಕ್ ಅಪ್ ದ ಫಸ್ಟ್ E4 system. It's an octahedral system and strong ligand field is present. That means now we have to go by crystal field approach, not VBT approach. Crystal field theory approach. Octahedral complex ge T2G EG ಈ ತರ ಸ್ಪ್ಲಿಟ್ಟಿಂಗ್ ಆಗುತ್ತೆ. D4 ಅಂತ ಹೇಳಿದ್ರೆ first 3 electrons like this, the field is very strong ligand field is present. ಅಂದ್ರೆ ಈ ಗ್ಯಾಪ್ ತುಂಬಾ ಎನರ್ಜಿ ಗ್ಯಾಪ್ ತುಂಬಾ ಹೈ ಇರುತ್ತೆ. ಇಲೆಕ್ಟ್ರಾನ್ ಮೇಲೆ ಹೋಗುವ ಬದಲಿಗೆ 4ನೇ ಇಲೆಕ್ಟ್ರಾನ್, ಓಕೆ, ವಿ ಆರ್ ರೈಟಿಂಗ್ ಅ D4 ಸಿಸ್ಟಮ್, 4ನೇ ಇಲೆಕ್ಟ್ರಾನ್ ಮೇಲೆ ಹೋಗುವ ಬದಲಿಗೆ ಪೇರ್ ಅಪ್ ಆಗ್ಲಿಕ್ಕೆ ಇಷ್ಟಪಡುತ್ತೆ. ಹಾಗಾಗಿ ನಂಬರ್ ಆಫ್ ಅನ್ಪೇರ್ಡ್ unpaired electrons is 2. So this itself is the answer, is it not? Mu 2.84 bm ಬರಬೇಕಿದ್ರೆ n 2 ಬರಬೇಕಾಗಿತ್ತು. ಸೊ ಇದರಲ್ಲಿ ಬರ್ತಾ ಇದೆ. This is the answer, but let's check the other options also. Let's check for the D3 system. For a D3 system and weak, also strong. Weak ಅಥವಾ strong here is immaterial. 3 electrons ಇರುವ ಕಾರಣ weak ಇರಲಿ strong field ಇರಲಿ ಇದೇ ತರ ಅದು ಅರೇಂಜ್ ಆಗುತ್ತೆ. Here the value of n is 3. 3 unpaired electrons. Value of n is 3. Next, let's check with the D4 octahedral. You have a weak field ligand, ಅಂದ್ರೆ ಈ ಗ್ಯಾಪ್ ತುಂಬಾ ಕಡಿಮೆ ಇದೆ. 3 electrons ಇಲ್ಲಿ ಬರುತ್ತೆ. 4ನೇ electron ಗ್ಯಾಪ್ ಕಡಿಮೆ ಇರುವ ಕಾರಣ ಮೇಲೆ ಹೋಗುತ್ತೆ. And value of n becomes here 4. So these are wrong. Lastly, D5. and you have a strong ligand field. That means the gap is high. Electrons do not go up. They prefer to pair up. Pair agate D5 system alli illi. So only one unpaired electron is present. N is equal to 1. That is also wrong. So first option itself is the answer. Okay, option number 1 is the answer. Moving on to the next question. Which of the following will exhibit maximum ionic conductivity? Look at the first complex. If you write the ionization pattern for this particular complex, totally for 1 mole of the complex, how many moles of the ions you get? 4 potassium ions and 1 complex ion, that is 5 ions. And for the next, 1 complex ion and 3 chloride ions. So totally 4. And for the third, 1 complex ion and 2 chloride ions, totally 3. And for the last, only 1 particular species you get. Actually, no ionization can take place over here as this is a neutral complex. You only have the square bracket term here and nothing outside the coordination sphere. Okay. So, maximum ionic conductivity is observed in the case of the very first complex, where you are getting 5 moles of ions per mole of the complex. Let's check it with the answer key. Answer is option 1. And here are the hints. Okay, for the first complex 5 ions, for the second 4, for the third 3, and this particular entity remains as such. It doesn't ionize further. Matte ionize agudilla, adu whole agi ulitade. Coming to the next question, question number 17. Which of the following coordination compounds has a central metal atom obeying EAN rule? What is EAN rule? EAN rule is nothing but effective atomic number rule. What is the formula for EAN actually? EAN formula is atomic number of a central metal minus its oxidation number or oxidation state plus 2 into coordination number of the central metal. If this particular value comes out to be 36, then we say that EAN rule is obeyed. For most of the complexes, it is so. Okay, for most of the complexes, EAN value comes out to be 36, but some do not obey this particular rule. Now, let's see which complex obeys the EAN rule and which doesn't obey it. Look at the first complex. Iron is the central metal. Its atomic number is 26. And if you look at its oxidation state, it is 2. Iron is present in +2 form here. Okay. You have K4, Fe, Cn6. This is -6. This is +4. So, iron should be +2, is it not? To have a neutral complex, +6, -6. Neutral agbekidre, iron should be +2. So, oxidation number of iron is 2 here. Plus, there are 6 cyanidoligands, so that is why 2 into 6. 2 of the formula into coordination number 6. So, if you simplify, the value will be 36. In the case of second complex, iron is present in +3 form. It's not present in +2 form. Okay, K3 ide, so illi +3 ಆಗ್ತದೆ. Hagagi, to make the complex neutral, iron kuda +3 form alle irbekagate. So 26 minus 2 alla, 26 minus 3 it is. So the answer comes out to be 35 if you simplify. For the last complex, the central metal is copper, atomic number 29. Copper illi plus 2 formal untu. This ammonia is neutral, sulfate is minus 2, no? That is why copper should be plus 2. Minus 2 on a neutral malike, copper should be plus 2. So, oxidation state is 2 here, plus 2 of the formula into, coordination number is 2 illi, copper idu, it is 4. 4 ammonia ligands iruva karana 4. Simplify ಮಾಡಿದಾಗ 35 ಬರುತ್ತೆ. So EAN rule ಅನ್ನು obey ಮಾಡ್ತಾ ಇರೋದು ಫಸ್ಟ್ ಕಾಂಪ್ಲೆಕ್ಸ್ ಮಾತ್ರ. ಓಕೆ, ಸೆಕೆಂಡ್ ಆ್ಯಂಡ್ ಥರ್ಡ್ obey ಮಾಡೋದಿಲ್ಲ, ಎಲ್ಲದೂ obey ಮಾಡ್ತಾ ಇಲ್ಲ, only the first complex is obeying EAN rule. That is why option 1 is the answer. So this is a question on optical isomerism. Which of the following complex species is not expected to exhibit optical isomerism? Have a look at the first complex. It is of the type MAA3. Okay, MAA3. What does the AA stand for? It stands for a bidentate ligand. EN, okay, is a bidentate ligand. Ethane 1,2-diamine, is it not? It's a bidentate ligand, just like your oxalato ligand. Ox is also a bidentate ligand. Bidentate ligand na bariyuva krama hige. We write it as AA. Illi eradu ligands ide anta artha alla. It's a bidentate ligand. Antadu 3 ide. Okay, now if you write it's a structure, this is an octahedral complex, is it not? Bidentate ligands 3 ide anta helidre, denticity, I mean coordination number becomes 6. So octahedral complex aaytu idu. This is 1 AA, this is 2 AA, and here is your third AA. This is the structure of the complex. Now this complex cannot have a plane of symmetry, is it not? ಇದರಲ್ಲಿ ಈ ಕಾಂಪ್ಲೆಕ್ಸ್ ನಲ್ಲಿ ಯಾವುದೇ ರೀತಿಯಲ್ಲಿ ಒಂದು ಪ್ಲೇನ್ ಆಫ್ ಸಿಮೆಟ್ರಿಯನ್ನ ಇಮ್ಯಾಜಿನ್ ಮಾಡಲಿಕ್ಕೆ ಸಾಧ್ಯ ಇಲ್ಲ. ಸೊ ನೋ ಪ್ಲೇನ್ ಆಫ್ ಸಿಮೆಟ್ರಿ, and therefore the complex is optically active. ಇದು ಆಪ್ಟಿಕಲ್ ಆಕ್ಟಿವಿಟಿಯನ್ನ, ಆಪ್ಟಿಕಲ್ ಐಸೋಮೆರಿಸಮ್ ಅನ್ನ ತೋರಿಸ್ತದೆ. ಇದರ ಪಕ್ಕದಲ್ಲಿ ನೀವು ಒಂದು ಮಿರರ್ ಇಟ್ರೆ ಆಗ ಮಿರರ್ ಇಮೇಜ್, how does it appear? If you place a mirror in front of this complex, then the mirror image will appear, okay, the mirror image will appear like this, AA, AA, and AA. So this is D form and this is L form. These are optical isomers of this particular complex. Okay, so option 1 is not surely the answer. This is ruled out. Coming to the next option. This is of the form MAA2, is it not? Again we have a bidentate ligand, so MAA2, and this is B2. Chlorine anna B anta ತಗೊಂಡಿದ್ದೇನೆ, B2. ಇದರ ಸ್ಟ್ರಕ್ಚರ್ ಹೇಗೆ ಬರೀತೀರಾ? M octahedral complex, okay, and let me write 1 AA here, another AA here, and this is B, this is one more B. Now actually what I have written is the transform anna bardidene, is it not? Same ligands are present on the opposite sides, transform bardidene, and clearly you can see that there is a plane of symmetry. ಈ ತರ ಒಂದು ಪ್ಲೇನ್ ಅನ್ನ ನೀವು ಪಾಸ್ ಮಾಡಿದ್ರೆ ಮಾಲಿಕ್ಯೂಲ್ ನ ಮೂಲಕ ಅದು ಮಾಲಿಕ್ಯೂಲ್ ಅನ್ನ ಎಕ್ಸಾಕ್ಟ್ ಎರಡು ಹಾಫ್ ಆಗಿ ಡಿವೈಡ್ ಮಾಡುತ್ತೆ. ಸೊ ಬಿಕಾಸ್ ದರ್ ಇಸ್ ಅ ಪ್ಲೇನ್, symmetry plane, what happens? The transform is optically inactive. Plane of symmetry iruva karana transform is optically inactive. But what about the cis form? Let me write the cis form here. AA, AA, BB. Okay, the two B's are very close and the two bidentate ligands are also close to each other. They are at the adjacent positions. So this is the cis form. Now in the cis form, you do not have any plane of symmetry. Transformal ittu symmetry plane, but illi symmetry plane illa. Hagagi enagate, this is optically active. Okay, cis form is optically active. This option is ruled out. It is optically active. This option is also ruled out because transformer inactive ಆದ್ರೂ ಕೂಡ cis form optical activity ಅನ್ನ ತೋರಿಸ್ತಾ ಇದೆ. ಹಾಗಾಗಿ ಸೆಕೆಂಡ್ ಆಪ್ಷನ್ ಕೂಡ ರೂಲ್ ಔಟ್ ಆಯಿತು. Now let's go to the third complex. The third complex is of the form MA3B3. ಇಲ್ಲಿ bidentate ligands ಇಲ್ಲ, ಎಲ್ಲ monodentate ligands ಇರೋದು. So MA3B3 form ಅಲ್ಲಿ ಇದೆ. It can actually show cis and trans isomerism, but we do not call them cis and trans. Instead, we call them facial and meridional isomers. How does the facial form appear? Central metal is here. AAA written continuously and then BBB. So this is the facial form. And this particular facial form, which is similar to your cis form in other complexes, there is a plane of symmetry. If you pass a plane through the molecule like this, okay, along this axis, A and B axis, then the molecule will be cut into two exact halves. So plane of symmetry ide. That is why it is optically inactive. This particular form is optically inactive. Coming to the meridional form. AA, B, BB, A, and then comes a B. So the continuity is lost here. We don't write the three A's continuously. Two A's are written and then a B. Once again a B, A and B. Meridional form is written like this. Three A's and three B's are there. Now, this also has a plane of symmetry. If you have a closer look at this particular molecule, then you will see that there is a plane of symmetry in the molecule along this particular plane. This is the plane of symmetry. Okay, ಈ ಪ್ಲೇನ್ ಇದೆ ಅಲ್ಲ, ಎ ಮೆಟಲ್ ಎ ಮತ್ತೆ AB ligands ಅನ್ನ ಹೊಂದಿರುವ ಪ್ಲೇನ್ ಇದೆ ಅಲ್ಲ, that actually cuts the molecule into two halves. Okay, one ligand B is present above the metal, the other ligand B is present below the metal, below the plane. So this is the plane of symmetry. ಇಲ್ಲಿ ಕೂಡ plane of symmetry ಇದೆ. And symmetry element iruva karana, this molecule, this form of the molecule is also optically inactive. Idu matra alla, facial form matra alla, meridional form kuda optically inactive ಆಗ್ತದೆ. ಹಾಗಾಗಿ this one is the answer. Okay, the species that doesn't exhibit optical isomerism is this. This is the answer. But let's look at the last option also. It is of the form M, again a bidentate ligand AA, B twice, C twice. So this is the form of the complex. Now, if you write the structure, this is AA, and B and B here along this axis, C and C here. This is actually the trans form of the molecule. Okay, two B's are on the opposite side of the metal. And how do you write the cis form? Two B's are very close to each other. Similarly, two C's are adjacent to each other. So this is the cis form. Now here, the trans form has a plane of symmetry. Which is that plane? The plane is actually the plane which passes through the complex like this. Okay, this is that plane. This particular plane cuts the molecule into two equal halves. Or you can even imagine a plane perpendicular to this plane like this. Okay, that also cuts the molecule into two equal halves. So there is a plane of symmetry and the molecule is optically inactive. But such a plane is not observed here. Okay, such a plane of symmetry is not present here. You cannot have this as a plane. Idanna plane age tagollikagalla because aga one side you have B, the other side you have C. Two equal halves age cut agalla molecule. Similar plane illi imagine malikagalla. So cis formally plane illa, symmetry plane illa. Hagagi this is optically active. So this option is also ruled out. Cis formally optical activity iruva karana, this option is ruled out. So option number 3 is the right answer. Yeah. Which kind of isomerism is shown by the complex that is given? It's a complex of the form metal, 4 ligands of one type and 2 ligands of the other type. Ma4B2 complex it is. Now, clearly this particular complex exhibits cis-trans isomerism, that is geometrical isomerism. Which are the geometrical isomers? You have one cis isomer and you have one trans isomer. This is the cis isomer, okay? B and B are adjacent to each other and the trans isomer is this. B and B are opposite to each other. Cis ಮತ್ತೆ trans isomers, geometrical isomerism ide. ಈಗ trans isomer nalli it's very clear that there is a plane of symmetry, is it not? If you pass a plane through the molecule like this, there are many planes of symmetry. One example is this. So this is a plane of symmetry. Therefore, this is optically inactive. It doesn't show optical activity. Plane of symmetry is there. What about the cis form? Cis form nalli kuda there is a plane of symmetry. Now, which is that plane of symmetry in the case of cis form? The symmetry plane, again, there are more than one symmetry planes. One of them is this. It is you can have a plane like this, okay? This particular plane which involves MABAB, okay? This plane involving MABAB divides the molecule into two equal halves. One ligand is above the plane, ligand A, the other ligand A is below the plane. So illi kuda plane of symmetry ide. and therefore this molecule is optically inactive. Geometrical isomerism untu, but optical isomerism illa. What about the ionization isomerism? Ionization isomerism is present in this particular complex. Which are the ionization isomers that you have? See, these are the two ionization isomers. What you have to do is you have to take one bromine outside and the chlorine inside. Exchange of ligand and the counter ion has to be done. ಒಂದು ಬ್ರೋಮಿಡೋ ಲಿಗ್ಯಾಂಡ್ ಅನ್ನ ಹೊರಗೆ ತಂದು ಕ್ಲೋರೈಡ್ ಕೌಂಟರ್ ಅಯಾನ್ ಅನ್ನ ಒಳಗೆ ತಗೊಂಡು ಹೋದ್ರೆ okay, you get ionization isomers. That is why the complex exhibits geometrical isomerism and it exhibits ionization isomerism but not optical isomerism. Option 1 is the answer. Again a question on metal carbonyl. If the bond length of CO bond in carbon monoxide is 1.128 angstrom, carbon monoxide has a triple bond between carbon and oxygen. So this bond length is given 1.128 angstrom. What is its value in FeCO5? That is iron pentacarbonyl. Iron pentacarbonyl nalli kuda e bond length same ulitada athwa whether it is different, that we have to answer now. What happens in the case of iron pentacarbonyl? There is a bond, there comes a bond between iron and carbon. Carbonyl matte iron na naduve, carbon matte iron na naduve, there comes a bond. Metal carbon bond comes, and because of the presence of this metal carbon bond, what happens is, already in one of the previous questions it has been told to you that this particular bond becomes weak. The metal carbon interaction nindagi in two ways they interact, is it not? Ligand gives electrons to metal and metal also gets involved in back bonding. It gives its electrons to the ligand. So when they interact in two ways, when there is an interaction between metal and carbon, the carbon-oxygen interaction becomes weak, and whenever the interaction becomes weak, the length, the bond length becomes more. Bond length value becomes higher than the normal. What is the normal bond length? It is triple bond length is 1.128 angstrom. Iga metal carbonyl nalli ee value jasti agbeku. That means this is the answer. Illi value same ide. Is it not? And this value is less. Okay. 1.72 angstrom is too high. Okay, 1.72 angstrom is too high. So the answer has to be what? It is 1.15 angstrom, slightly higher. Okay, slightly higher than the normal triple bond length. Due to metal carbon bonding, CO bond becomes weak and the bond length increases. 1.128 kinta value ಸ್ವಲ್ಪ ಜಾಸ್ತಿ ಆಗುತ್ತೆ. So 1.15 is the answer. ಇಲ್ಲಿ ಕಡಿಮೆ ಆಗಿದೆ, ಇಲ್ಲಿ ಸೇಮ್ ಇದೆ. This value is very very high, okay, which cannot be the answer. It is slightly higher, that is why this is the answer. Among the following, the compound which absorbs light in the visible region. It is the other way of asking the question like this. Which of the following compounds is colored? Compound visible region nalli light anna absorb ಮಾಡ್ತಾ ಇದೆ ಅಂದ್ರೆ ಅದರ ಅರ್ಥ that particular compound has color. So colored compound you need to choose from these options. All of these compounds are the compounds of copper. In the first case, copper is present in +1 form. Cl is -1, copper is +1. In the second case, copper is present in which state? This is -4, this is +3. So copper again is present in +1 form only. Third compound has copper in 2+ form. Okay, this is -2, so copper should be +2. And in this particular compound, see, this is a neutral ligand. This is nothing but ethane nitrile. Okay, CH3CN is ethane nitrile athwa methyl cyanide. It's a neutral molecule, neutral ligand. So charge illa. BF4 has -1 charge. So copper should have +1 charge. Mooru compounds alli copper is present in +1 form. Only in the third compound copper is present in 2+ form. Cu plus is a D10 system. Correct? Cu plus is a D10 system and Cu2 plus is a D9 system. In D10 system, DD transition is not possible because all the 5d orbitals are occupied with the electrons because there is no space for DD transition to occur or take place. No DD transition is possible. Only in the case of D9 you can expect a DD transition to take place, which results in the color. That is why Cu2 plus, that is option number 3, is a colored compound, or in other words, it is the one which absorbs light in the visible region. So option 3 is the answer. Okay. Next question, 22nd question. A question on isomerism, geometrical isomerism actually. The total number of geometrical isomers for the complex. This is a complex of rhodium. I'll take it as M. There is a chlorido ligand, carbonyl ligand, then triphenyl phosphine, PPH3 anta helidre, triphenyl phosphine ligand. I'll denote it as C, and ammonia or ligand name is amine. I'll denote it as D. So all 4 different types of ligands are present in this particular complex. So the complex is of the form MABCD. Now, how many geometrical isomers it has? This particular complex actually has 3 geometrical isomers, out of which 2 are cis and 1 is trans. Now, how to arrive at those 3 isomers? Let us see. At the center, there is a metal M. I'll write the ligands A and B here, okay? And I'll make an assumption that A and B ligands, okay, they are almost similar to each other. Of course, they are not exactly the same. Exactly same ididre adana AA athwa BB anta barita idvi, but almost similar ide anta ankolona. So A and B, and then what remains is C and D. This is one form. Because I have assumed that A and B are similar ligands, okay, because I have assumed that A and B are similar ligands, this is a cis form. Similar ligands hatra bandre, okay, if they are on one side, it's a cis form. Now what I'll do, I'll keep A and B on this side only, and I'll exchange C and D. C matti D positions anna interchange martene. D comes here and C goes here. This is also a cis form, alva. A matti B change madilla. Similar ligands hatra hatrane ide, one side nalle ide. So this is also a cis form. These two are not exactly the same. Ideredu bere bere ಮಾಲಿಕ್ಯೂಲ್ಸ್, ಬೇರೆ ಬೇರೆ ಕಂಪೌಂಡ್ಸ್, ಒಂದೇ ಕಾಂಪ್ಲೆಕ್ಸ್ ಇದ್ದು ಫಾರ್ಮ್ಸ್ ಇರ್ಬೋದು, ಬಟ್ ದೇ ಆರ್ ಡಿಫ್ರೆಂಟ್. Why they are different? Why they are not the same? Because you see, you concentrate on A ಮೇಲೆ ಕಾನ್ಸಂಟ್ರೇಟ್ ಮಾಡಿದ್ರೆ A ಯ ಒನ್ ಸೈಡಲ್ಲಿ ಯು ಹ್ಯಾವ್ C, ಅದರ್ ಸೈಡಲ್ಲಿ B ಇದೆ. ಆದರೆ ಇದರಲ್ಲಿ A ಯ ಒನ್ ಸೈಡಲ್ಲಿ B ಇದೆ, ಮತ್ತೊಂದು ಸೈಡಲ್ಲಿ D ಇದೆ. Okay, so these two forms are not the same, they are different, both of them are cis forms. Now what I'll do, I'll keep the similar ligands on opposite sides. A ಮತ್ತೆ B ಅನ್ನು ನಾವು ಸಿಮಿಲರ್ ಅಂತ ಅಸ್ಯೂಮ್ ಮಾಡಿರೋದಲ್ವಾ, ಈಗ ಅದನ್ನ ಆಪೋಸಿಟ್ ಸೈಡ್ಸ್ ಅಲ್ಲಿ ಇಡ್ತೇನೆ. ಓಕೆ, ಅಂಡ್ ರಿಮೈನಿಂಗ್ 2 ligands ಇದೆ ಅಲ್ಲ, C ಮತ್ತೆ D, ಅದನ್ನ ಇನ್ನುಳಿದ ಸೈಡ್ಸ್ ಅಲ್ಲಿ ಇಡ್ತೇನೆ. Now this is which form? This is without any doubt trans. A ಮತ್ತೆ B similar ligands, okay, exactly same ಅಲ್ಲ, almost similar, they have come to opposite sides, that is why this is transform. ಈಗ ಈ C ಮತ್ತೆ D ಯನ್ನ ಎಕ್ಸ್ಚೇಂಜ್ ಮಾಡಬಹುದು. What happens then if you exchange C and D? Here comes D, here comes C, but that is not going to change anything. ಅದು ಇನ್ನೊಂದು ಮಾಲಿಕ್ಯೂಲ್ ಅನ್ನ ಕೊಡುವುದಿಲ್ಲ. ಇಲ್ಲಿ CD ಇದ್ರೂ ಒಂದೇ ಅಥವಾ DC ಇದ್ರೂ ಒಂದೇ, ಯು ಆರ್ ಗೋಯಿಂಗ್ ಟು ಅರೈವ್ ಎಟ್ ದ ಸೇಮ್ ಮಾಲಿಕ್ಯೂಲ್. ಯಾಕೆ? ಬಿಕಾಸ್ A ಯ ಒನ್ ಸೈಡಲ್ಲಿ C ಇರುತ್ತೆ, ಇನ್ನೊಂದು ಸೈಡಲ್ಲಿ D ಇರುತ್ತೆ. ಈಗ ಇಲ್ಲಿ D ಬರೆದ್ಬಿಟ್ಟು ಇಲ್ಲಿ C ಬರೆದ್ರೆ ಆಗ ಕೂಡ on one side A will have C, the other side A will have D. Okay, it's not going to make any difference. You are not going to arrive at an additional transform. Cis ಅಲ್ಲಿ ಮಾತ್ರ ಎರಡು ಬೇರೆ ಬೇರೆ ಫಾರ್ಮ್ ಸಿಗುತ್ತೆ ನಿಮಗೆ, ಆದರೆ ಟ್ರಾನ್ಸ್ ಅಲ್ಲಿ ಯು ಆರ್ ಗೋಯಿಂಗ್ ಟು ಗೆಟ್ ಓನ್ಲಿ ಒನ್ ಫಾರ್ಮ್. Exchanging the positions of C and D is not going to change anything. That is why totally 2 cis and 1 transforms, 3 geometrical isomers are possible, and option 3 is the right answer. Okay. Next is the question on crystal field stabilization energy. The formula for crystal field stabilization energy in the case of octahedral complexes. Okay, the question is on octahedral complexes. So the formula becomes minus 0.4 T2G. T2G is the lower energy set, is it not? Plus 0.6 Eg. Eg is the higher energy set into delta O. In the case of tetrahedral complexes, it's going to be different. The formula is going to be different. What happens there is Eg comes down in the energy axis, T2G goes up. Hagagi formula dalli kuda minus 0.6 Eg agate plus 0.4 T2G agate. Okay, the formula changes. This is only for delta O. I mean for octahedral complexes. Now the system is a D4 system. How do you write a D4 system? It is T2G 3 and Eg 1. Why don't you carry out pairing here? Because it is mentioned that the complex is a high spin complex. High spin complex anta mention madidare, andre spins free irbeku, pairing agbardu. Hagagi illi pair madlilla nanu 4ನೇ electron anna I have written it here. So this is the configuration T2G3 and Eg1. Now if you substitute in the formula, what happens? Actually here T2G stands for the number of electrons in T2G. Okay, so if I substitute, it becomes minus 0.4 into 3, is it not? There are 3 in T2G plus 0.6 into 1 in Eg. Okay, delta O. So that will minus 0.4 into 3 plus 0.6 into 1 Okay. If you simplify, this is minus 1.2, this is 0.6. Simplification further will give you minus 0.6 delta O. And minus 0.6 delta O is the fourth option, which is the right answer. Okay. The next question is a question on pi bonded organometallic compounds. Now you have to do here a selection of the complex which is not a pi bonded organometallic compound. What is a pi bonded organometallic compound? In such compounds, the ligands will have pi bonds in them. For example, look at the first complex. You have a benzene as the ligand. And you know very well benzene has got pi bonds in it. Now, what is the meaning of this eta? This is pronounced as eta, eta 6. Eta stands for hapticity, and eta 6 means 6 atoms, 6 carbon atoms. Okay, 6 carbon atoms of the benzene ring which are involved in pi bonding. They are involved in interaction with the chromium metal. ಎಲ್ಲ 6 atoms ಬೆನ್ಝೀನ್ ಇದ್ದು ಕ್ರೋಮಿಯಂನ ಜೊತೆಗೆ ಬಾಂಡಿಂಗ್ ಅಲ್ಲಿ ಇನ್ವಾಲ್ವ್ ಆಗಿದೆ. ಹಾಗಾಗಿ ನಾವು ಈಟಾ 6 ಹ್ಯಾಪ್ಟಿಸಿಟಿ 6 ಅಂತ ತೋರಿಸ್ತೇವೆ. Okay, so this is a pi bonded compound, is it not? Because there are pi bonds. In the second compound, you have a methyl group, CH3 group. You know very well it doesn't have any pi bonds. Methyl group alli yavade pi bonds illa. Look at the third compound, you have C6H4 ligand. That C6H4 is nothing but benzene. Benzene is this. Benzene has an additional pi bond. Okay, this is benzene. There is a triple bond between these two carbons. And ಈ ಎರಡು ಕಾರ್ಬನ್ ಆಟಮ್ಸ್ ಮೆಟಲ್ ನ ಜೊತೆಗೆ ಇಂಟರಾಕ್ಷನ್ ನಲ್ಲಿ ಇನ್ವಾಲ್ವ್ ಆಗಿದೆ. ಸೊ ವಿ ಸೇ ಹ್ಯಾಪ್ಟಿಸಿಟಿ ಇಸ್ 2. ಓಕೆ, ಹ್ಯಾಪ್ಟಿಸಿಟಿ ಹಿಯರ್ ಇಸ್ 2. ಈ ಎರಡು ಆಟಮ್ಸ್ ಪೈ ಬಾಂಡೆಡ್ ಆಟಮ್ಸ್ ಆರ್ ಇನ್ವಾಲ್ವ್ಡ್. ಸೊ ಇದರಲ್ಲಿ ಕೂಡ ಪೈ ಬಾಂಡ್ ಇದೆ. ಇದರಲ್ಲಿ ಇದೆ. ಇವನ್ ದಿಸ್ ಆಪ್ಷನ್ ಹ್ಯಾಸ್, ದಿಸ್ ಆಪ್ಷನ್ ಡಸಂಟ್ ಹ್ಯಾವ್ ಪೈ ಬಾಂಡ್. And what about the C5H5? It is cyclopentadiene. Cyclopentadiene anna hege baritira? A pentagonal ring, okay, 2 pi bonds. So all the 5 carbon atoms, okay, all the 5 carbon atoms are involved in bonding with the metal. That is why hapticity here is 5. All right. Now, because these 3 are having pi bonds in the ligands, they are not the answers. Only the second option, which doesn't have any pi bond, becomes the answer. So option 2 is the right answer. Next question, in an octahedral structure, the pair of d orbitals involved in D2sp3 hybridization. See, when D2sp3 hybridization takes place, n minus 1 d orbitals will be involved in bonding. Actually, there are 5 such orbitals. 3 of them will be having electrons. Is it not? 3 of them will be having electrons of the metal, and these 2 D2sp3 alli baruva. This is D2, this is yes, and these 3 p orbitals make it D2sp3. ಈ 3 orbitals alli metal ina electron irutte. Metal electrons irutte. They may be all paired or some of them may be single. It all depends. These hybrid orbitals, okay, D2sp3 andre ee tara irutte. Ee hybrid orbitals alli yava electrons irutte? There will be ligand electrons coming from the ligands. Is it not? So now, the question is, in an octahedral structure, the pair of d orbitals involved in the hybridization. Hybridization nalli involve ಆದದ್ದು ಯಾವುದು? These two, correct? Not these three. These three are not involved in hybridization. Instead, these two are involved in hybridization. Now, actually, if you expand this particular D set and write, it is T2G and EG. Okay, octahedral nalli ee tara crystal field splitting ಆಗುತ್ತೆ. T2G lower energy, EG higher energy. T2G ಅಲ್ಲಿ ಮೆಟಲಿನ electrons ಇರುತ್ತೆ. Metal electrons will be present. It will not be involved in hybridization, but EG ಯ ಎರಡು orbitals ಏನಿದೆ ಅದು ligand electrons ಅನ್ನ accommodate ಮಾಡುತ್ತೆ. So it is this which is involved in hybridization, not T2G but EG. EG set comprises of what? X square minus Y square and DZ square. Is it not? Higher energy set comprises of dx square minus y square and dz square. This lower energy set has dxy, dyz and dxz orbitals. So hybridization alli idu illa, only this is involved, EG set is involved, or in other words, these two orbitals are involved. So very first option is the answer. Option number 1 is the answer. What is the correct electronic configuration of the central atom based on crystal field theory? It's an octahedral complex. So you will have to do this splitting EG, T2G, crystal field approach. Okay, the splitting has to be shown. And which is the metal present? Fe. If you look closely, it is Fe2 plus. Iron is 3d6, so 4 is 2, but in the 2 plus form, these two electrons are lost, 3d6. Cyanide is a strong field ligand. Hagagi, electron pairing prefer agate. This is the configuration that you will have. All the 6 electrons will be accommodated in T2G. EG ge electrons hogudilla because cyanide strong field ligand ಆದ ಕಾರಣ ಇಲ್ಲಿ energy gap will be very high. ಮೇಲೆ ಹೋಗುವುದರ ಬದಲಿಗೆ electrons prefer to pair up. So T2G6, okay, T2G6 and EG0 is the answer. Option 4 is the answer. Next is a question on dissociation, equilibrium constant and overall stability constant. A complex becomes highly stable if at all its overall stability constant value is very high. Now, what is the formula for overall stability constant of the complex? It is nothing but 1 by dissociation equilibrium constant. Remember, the two constants are inversely related. They are the reciprocals of one another. Now, dissociation constant value is given. It is 2.3 into 10 to the power minus 9. If you take the reciprocal, it becomes 10 to the power plus 9. And if you approximate it to 2, 2.3 and 2 anta illi tagondre 1 by 2 andre half, it is nothing but 0.5. So answer 0.5 ge hatradalli irutte. 0.5 into 10 power 9. 0.5 into 10 power 9 because the decimal point options alli decimal point ಒಂದು place ನಂತರ ಇರುವ ಕಾರಣ I'll do a similar rearrangement here. Decimal point ಅನ್ನು ಇಲ್ಲಿ ಮುಂದೆ ತಗೊಂಡು ಹೋಗುವಾಗ 5 into what happens is 10 power 9 becomes 10 power 8. ಡೆಸಿಮಲ್ ಪಾಯಿಂಟನ್ನು ಒಂದು ಪ್ಲೇಸ್ ಮುಂದೆ ಶಿಫ್ಟ್ ಮಾಡಿದಾಗ ಇಲ್ಲಿ 9 minus 1 ಮಾಡಿ 10 power 8 ಆಗುತ್ತೆ. All right, so the answer that is close to this is option number 4. Option number 4 is the answer. Okay, because you do not have calculators, you can approximate the values to the nearest integers and you can do the calculation. All right, next question, 28th question. It's a question on IUPAC nomenclature of the complex. Whenever we do IUPAC nomenclature, what we do is we write the name of the cation first and then the anion. Here the cation is potassium. Okay, potassium. But remember one thing, whatever comes outside the square bracket is written by its name without adding any prefixes like di, tri, etc. ಈಗ ಇಲ್ಲಿ 2 potassium ಇದೆ ಅಂತ ಹೇಳಿ dipotassium ಅಂತ ಬರೆಯುವ ಹಾಗೆ ಇಲ್ಲ. Okay, you have to just write potassium. ಈಚೆ ಸೈಡ್ ಅಲ್ಲಿ ಮಾತ್ರ ಅಲ್ಲ, sometimes you get the counter ions on the right side, anionic ಪಾರ್ಟ್ ಆಗಿ ಹೀಗೆ ಸಿಗುತ್ತೆ. ಆಗ್ಲೂ ಕೂಡ 3 chlorines ಇದ್ದಾಗ you cannot write trichloride. Such prefixes can be used only for the ligands, remember, not for the counter ions. This has to be written as chloride. So here it is potassium, not dipotassium. Okay, so all the 4 options have potassium, so that's not going to help. Next, square bracket term ಅಲ್ಲಿ ligands ಅನ್ನ first name ಮಾಡಬೇಕು ಮತ್ತೆ central metal ಗೆ ಬರಬೇಕು alphabetical order ಅಲ್ಲಿ. So this is amine ligand. Okay, this is amine. This is cyanido, ಎರಡಿದೆ ಅಂತದ್ದು dicyanide. What about O? This is oxido ligand. O is actually O2 minus oxido ligand ಅಂತದ್ದು ಎರಡಿದೆ. So dioxido, amine, dicyanide, dioxido. And which is this ligand? O2. It actually has a charge of 2 minus, O2, 2 minus. This is oxido, ಎರಡಿರುವ ಕಾರಣ dioxido ಆಯಿತು. This is peroxido ligand. There is only one such ligand present. Okay, ಇದು ಎರಡಲ್ಲ, ಇದು ಒಂದೇ ligand. O2, 2 minus is one ligand, peroxido ligand. All right, so amine, dicyanide, dioxido, peroxido. And then coming to the central metal. Central metal is chromium. But anionic complex ಆಗಿ ಬಂದಿದೆ ಅಲ್ಲ, anionic part ಆಗಿ ಬಂದಿದೆ ಅಲ್ಲ chromium. ಹಾಗಾಗಿ we have to write it as chromate. Okay, chromium ಬರೆಯುವ ಹಾಗಿಲ್ಲ, chromate. So far the option 1 is it matches with our answer. Now let's check the oxidation state once. ಅದು ಕೂಡ ಮ್ಯಾಚ್ ಆದ್ರೆ option 1 itself is the answer. Oxidation state check ಮಾಡುವಾಗ you see this is +2, potassium +2, this is neutral, -2. This I told you 1 is 2 minus, ಎರಡಿದೆ ಹಾಗಾಗಿ -4. Peroxide is 2 minus, so totally it becomes how much? -2 minus 4 is -6, again -2 is -8, -8 and there is a +2 over here. So makes it -6. That is why chromium should be +6. Chromium anna X anta tagondre rest of the things, okay, -2, -4, -2. Idu -8 ಆಯ್ತು, ಇಲ್ಲಿ +2 ಇದೆ, ಅದು ಸೇರಿ -6 ಆಯ್ತು. So complex ಅನ್ನ neutral ಮಾಡಲಿಕ್ಕೆ chromium should have +6 state, or if you find it difficult this way, then you can take chromium state as X and you can solve it in a systematic manner and find out its state. So chromium is in a 6th state. So with that, option 1 is the correct IUPAC name for the complex. See, cyano cannot be used according to IUPAC rules. Cyanido has to be used. Remember, oxo can't be used, oxido has to be used. All right. So option 1 is the answer. the number of chelate rings in the particular complex. See, if a ligand binds to the central metal with the help of more than one donor atoms, then we say it is a chelating ligand. Actually, it forms a ring type structure around the central metal. That is why we call it a chelating ligand. Now, oxalato is a bidentate ligand, and it is forming actually the chelating rings around chromium. One oxalato actually forms a one ring. Okay. Now, how many oxalato ligands are present? There are 3 oxalato ligands. That is why 3 chelating rings are expected. How does the complex appear? This is chromium. It's an octahedral complex. So, one ox comes here, one ring. Another ox comes here, bidentate ligand. Okay, 2 bonds are formed. This is another ring, ring number 2. And here comes the third ox. This is the third ring. So, 3 rings are formed. Option 3 is the answer. Yeah. Each oxalato ligand forms one chelating ring. With that, totally 3 rings. 29th question is over. This is the last question, 30th question. It's a question on Jahn-Teller effect. Though there is J-A-H-N in the name, it's pronounced as Jahn-Teller effect. Now, which of the following complexes do not show Jahn-Teller effect? That is the question. First of all, let us see what is this Jahn-Teller effect. Actually, this is a phenomenon because of which in octahedral complexes, opposite bonds will either be elongated or compressed. The criterion for Jahn-Teller effect is that the configuration of the central metal in the complex should be unsymmetrical. Unsymmetrical configurations idre matra ee particular effect namge nodlikke sigutte. Now, let's take up D9 system. Because it is an octahedral complex and it is a high spin complex. High spin anta helidre enu? Free spin. Andre crystal field splitting ideyalla adu weak irutte. Pairing ideyalla adu nadiyudilla. ಅದರ ಬದಲಿಗೆ electrons spins free ಆಗಿ ಇರಲಿಕ್ಕೆ ಇಷ್ಟಪಡುತ್ತೆ. Okay, so D9 system, it's an octahedral complex. Splitting will be T2G, EG like this. Because it is D9, it doesn't matter whether you have weak ligand, strong ligand, alva high spin ಇದೆಯಾ, low spin ಇದೆಯಾ, ಅದು actually matter ಆಗಲ್ಲ. Configuration ಒಂದೇ ತರ ಬರೀಲಿಕ್ಕೆ ಆಗೋದು. ಹೇಗೆ ಅದು? This is how you write it, D9 ಗೆ. Now, look at the configuration. ಇದರಲ್ಲಿ symmetry ಉಂಟು. ಎಲ್ಲ 3 orbitals ಅಲ್ಲಿ 2 electrons ಇದೆ. But ಇದರಲ್ಲಿ symmetry ಇಲ್ಲ. ಇದರಲ್ಲಿ 2, ಇದರಲ್ಲಿ 1 electron ಇದೆ. ಹಾಗಾಗಿ this is unsymmetrical configuration and Jahn-Teller effect is seen here. D7 system, if you take, in D7 system, what happens? High spin complex alva, hagagi idu gap less irutte. Pairing prefer agudilla, electrons ಆದಷ್ಟು single ಆಗಿ ಇರಲಿಕ್ಕೆ ಇಷ್ಟಪಡುತ್ತೆ. So D7 ಹೇಗೆ ಬರೀತೀರಾ? 1 2 3. Instead of pairing, I'll take them to the EG set. 5 ಆಯಿತು. ಇನ್ನೂ 2 electrons ಇದೆ. So ಅದು ಬೇರೆ ವಿಧಿ ಇಲ್ಲದೆ ಇಲ್ಲಿ pairing ಆಗುತ್ತೆ. ಈಗ EG ಯಲ್ಲಿ ಸಿಮೆಟ್ರಿ ಇದೆ ಅಲ್ವಾ, ಒಂದೊಂದು ಎಲೆಕ್ಟ್ರಾನ್. ಬಟ್ T2G ಯಲ್ಲಿ ಸಿಮೆಟ್ರಿ ಇಲ್ಲ, 2 2 1. ಹಾಗಾಗಿ ಇದು ಕೂಡ Jahn-Teller effect ಅನ್ನ ತೋರಿಸ್ತದೆ. ಓವರಾಲ್ ಸಿಮೆಟ್ರಿ ಇಲ್ಲದ ಕಾರಣ Jahn-Teller effect is seen. So first 2 are not the answers. ಎರಡು Jahn-Teller effect ಅನ್ನ ತೋರಿಸುವ ಕಾರಣ they are not the answers. Let's check the last 2. One is D8, the other is D4, T2G and EG. How do you write D8? Keeping in mind that this gap is less. So 1, 2, 3, then electrons go up, 4 and 5, 3 more, they get paired up. Okay, symmetry here, here also there is symmetry. Therefore, this is not expected to exhibit, okay, this is not expected to exhibit the phenomenon. Symmetry ಇದೆ, overall symmetry ಇದೆ, T2G ಅಲ್ಲೂ ಇದೆ, EG ಅಲ್ಲೂ ಇದೆ. D4 ಅಲ್ಲಿ, this gap is low, no? This gap is less, that is why 3 here, and because the gap is less, the electron goes to this. Okay, now there is no symmetry in EG. Okay, symmetry EG ಅಲ್ಲಿ ಇಲ್ಲ, but T2G ಅಲ್ಲಿ there is symmetry. Overall symmetry ಇಲ್ಲ ಅಂತಲೇ ಹೇಳ್ಬೋದು. So ಇಲ್ಲಿ Ion Teller effect ಇದೆ. So only in this particular configuration the effect is not seen. That's why D8 is the right answer. Okay, option 3, D8 is the right answer. Alright, so with that we have finished all the 30 questions of coordination compounds. I hope this session was useful to you all. I thank you all for the opportunity given. Thank you again.